Okay, on to 7.2. So 7.2 is where things start to pick up a little bit. We're looking at the disk method, so solids of revolution or rotation. It'll depend on the word they use. Before we get into that, though, let's look into this paper, see if this helps. Let's look at volume in general. So if you guys remember the volume of a rectangular prism, it's capital BH, where capital B is the area of the base. So here's how I want you to think about it. Look at this picture over here. You can see that this yellow is the base. So this is the bottom. And then can you imagine like a ream of paper, right? So you have paper stacked, so a whole bunch of thin layers of paper. That does have volume. You would find the area of the bottom and multiply it by h, which is the height. That's what we're going to be looking at today, is taking like thin slices. So imagine paper thin slices of the areas that we're looking, or the volumes that we're looking at. Okay, so this one has a geometry formula. It has uniform shape, so it means like each piece of paper is the same. But what if you have this guy? So this is not the same, but I want you to think of it the same way. If we had the solid, if you could imagine paper, let's highlight this. So here's one piece of paper. So you have this piece of paper in the middle, and then you have a whole bunch of different papers slicing through this. Look at what the paper goes from A to B, just a small font right there. So we're going to be adding up an infinite number of these. Think about Riemann sum when you added up an infinite number of rectangles to get the area. Now we don't just have a rectangle, this actually has an area itself. So the volume formula that we're going to be looking at is, you can see where Riemann sum is coming back into play in terms of the idea. We're adding up an infinite number of areas. Okay, so right here, instead of doing Riemann sum in the limit process, how tedious all that was with I, we're going to look here instead. So we're going to add up an infinite number of areas. What if we had this? So what I'm going to have you do is whatever axis we're rotating around. So this is the x-axis. We'll do this. And imagine if we wanted to find this area. So think back to 7.1. We could draw rectangles, top minus bottom was generally our go-to, and we would have these rectangles. If we integrated the rectangles, we got the area. So integrating rectangles gives you area. Now what we're going to do is integrate area to get volume. Imagine this, and I showed you a visual in class. We looked at some websites where we could actually see this happening in 3D. So here you just got a picture. Imagine this rectangle attached here and swinging around. Okay, so this rectangle would be right here, and it would spin up and swing around, making a circle. So you have a circle swinging around here, and I put this picture here so you could imagine this. So this swings around to make a circle, so you have an infinite number of circles. If you can imagine this rotating, it would come down here and make like a cone. Okay, so we're adding up all of these circles. Okay, so let's see what this looks like. So disk method is what this is called. There's another method we'll learn in a couple days. Today we're going to look at disk. Again, revolution or rotation. This is a fun way to memorize it. Your rectangles have to be perpendicular to the axis of rotation. So before we go on, let me go over this. If this was my axis of rotation, do you see how my rectangles go this way? So remember, with area, we had a choice in some cases to make them vertical or horizontal. With disk method and volume, you don't. You have to go perpendicular to the axis of rotation. Okay, so that's going to be locked in for you. And perpendicular can be replaced with perpendicular to help you remember, because we're going to learn another method where they're parallel. So I just want you to know about this. The perpendicular, you can make it kind of fun and call it discular instead. You have circles. We saw that right here. I know I'm going back and forth a lot. You don't have to. You can just kind of look. But do you see this rectangle revolving to make a circle? So we're adding up an infinite number of circles. But instead of adding up an infinite number of areas, we can integrate. So if we are going around the x-axis, this is the x-axis. Let's look at this shape, and we'll call this region R. Your rectangles have to go perpendicular. So if this is your x-axis, your rectangles have to go this way. So they're locking in the top minus bottom idea. Why are they writing pi r squared? Like, does that remind you of something? Yeah, it's looking at the area of a circle. So what you're doing is you're taking this and revolving this around and getting an area of a circle. This is creating another circle. So you're adding up an infinite number of circles, and we know that the shortcut to that is to use integration. Okay, over here, if we're rotating around the y-axis, and now let's look at this. Oh, you know what? This said from A to B, so we should put an A to B here. This also says from A to B, so let's put an A to B here. If this is my axis of rotation, the rectangles have to be perpendicular, so they have to go this way. So they're going this way. So if you can imagine, this rectangle is swinging around and making a circle here. You have an infinite number of circles, and it will really make like this dome, where when this rotates this way, it makes like a sideways dome. Okay, let's try one of these. So find this volume rotated, let's see, of this region that's formed by the three functions listed to the right. Try to always graph the easier functions first, because that will limit how big your graph has to be. So for instance, y equals 0. We know we're looking at this. X equals 1. I'll write one off to the side because my line's going to go through it. We know we're looking at this. So we have this limitation and this limitation. So now when we go to graph the square root function, we know we don't have to go out to really big numbers. We're just going up to 1. So we have 0, 0, 1, 1. And look at your region. The line, the curve. This is f of x equals root x. Okay, so remember, we're not finding the area of this region. We're trying now to find the volume if we rotate this region about the x-axis. Here's the x-axis. Your rectangles have to be perpendicular to it. So if this is your axis, your rectangles go this way. Okay, and then we can set this up. So this is top minus bottom. The volume is pi. Remember, the formula is not going to be that bad, because if you can picture this revolving around making the circle, you know the area of the circle. It's pi r squared. If they get stacked vertically, they're always touching the x-axis, and x goes from 0 to 1. If these are x numbers, I need x number in here. Okay, so now look at the radii. They are constantly changing. Like here, the radius is 1. Here, the radius is 0. And here, somewhere in between 0 and 1. Whatever x is will determine the radius. So if x is 0.5, the height is the square root of 0.5. So x is going from 0 to 1. To find the radius, it's a function of x, because those are x. And it's just top minus bottom, which is what we did. So the top is root x, the bottom. This is the height of the rectangle, which is what you did in 7-1. Now we're squaring it, because the height of the rectangle becomes your radius. Pi is a scalar. I'll always write it in front. If you simplify this, you get x. If you integrate, you get x squared over 2 from 0 to 1, which is pi over 2. The integration, I feel, in this section is a lot easier. It's the setup I really want you focused on. And don't forget, on your assignment sheet, there's a handful of problems that all you have to do is set it up, Math 9 in your calculator, and get an answer. Okay, going on to another one. So we have this function. Now, let's see if we can zoom in a little. Again, I want you to graph the easier functions first. So y-axis is this. The line y equals 9. So now we know we're going up to 9. And the curve x squared. So if we're going up to 9, x would be 3. Let's see, that's 1. So we get this function right here. We don't need the whole thing, because remember, the y-axis is also a boundary. So we have this. They have to tell you what axis it's rotated around. In this case, it's the y-axis. Remember, perpendicular is perpendicular. So this is the disk method. So we're going perpendicular to it. So if this is your axis, there's your rectangle. Okay, so now v equals pi. Remember, we're integrating pi r squared because that's the area of a circle. We're going this way. Look at, if we're going right to left, horizontal, we're going this way all the way up to 9. So y goes from 0 to 9. Those are y values. If they're y values, I need x equal, because I want y in this. So if I solve for x here, I'm going to take the square root of both sides, plus or minus the square root of y. This is the square root of y, and this is the opposite of the square root of y. So it's the right side, which is root y, minus the left side. What's this equation? X equals root y minus x equals 0. This looks similar to the problem up above. We're really integrating y. We're going to get y squared over 2. Let's not forget the pi from 0 to 9, which is 81 pi over 2. And look at, if this rotates this way, you can see it just hits this. So it's like the bottom half of an egg as it starts going around. Okay, that gets us through the first page, front and back. First page is really just some ideas. Okay, now we're going to use our calculator on this one. So I just want us focusing on the setup here. Okay, so we are going to revolve negative x squared plus 2, y equals 0, and x equals 0 about the x-axis. So our graph, we have x equals 0 and y equals 0. So we have this and this. This curve, downward parabola, shifted up 2 units. This would be square root of 2. If this is 0, because we would want this whole thing to be negative 2. So we would kind of want this and this. And then because this is the boundary, here's our region. We're revolving it around the x-axis. Here's our axis. Rectangles are perpendicular. Okay, so our volume now. It's pi. These get stacked up on the x-axis. So we're going, remember this was root 2. So we're going from 0 to root 2. These are top minus bottom because they're vertical. The top is negative x squared plus 2. So y equals negative x squared plus 2 minus the bottom, which is y equals 0. Okay, and then actually I'm not going to do any more because we can use our calculator. So on this one, we can just type it in. We'll practice with that. Math 9. We're going from 0 to 2. And then what did we have? Negative x squared plus 2 all squared dx. And then, so that gives us our integral, but remember we also had pi. So once we type pi in, let's see, did we type something in wrong? Oh yes, this went actually to root 2, not 2. And then now let's try that times pi. There we go. Okay, 9.478. So I just typed a 2 on accident, went back and fixed it. So 9.478 would give us our volume here. Okay, we have another calculator problem over here. So we have the same region. I want you to see the difference between rotating around different axes and how it changes your answer. So because we already know what the graph looks like, I'm going to sketch it really quickly. This was 2, this was root 2, and this is our region. So now we're going around the y-axis, which means our rectangles are perpendicular to this. So now we're doing right minus left. This gets stacked up on the y-axis, so we're going from 0 to 2. These are y values, and let me go back and just point out those were x values. These are y values, so I have to solve this for x. So if you solve this for x, you're going to get x squared is 2x minus y. Did I write that wrong? X squared is 2 minus y. So then x is plus or minus the square root of 2 minus y. So this x is the square root of 2 minus y. This x is negative square root of 2 minus y. Right minus left, x equals this, so square root of 2 minus y, minus this curve, which is x equals 0, all squared. And I know we're allowed to just use our calculator, but we can see that this reduces pretty nicely. I'm going to go ahead and finish this one by hand. Pi is out in front. you get 2y minus y squared over 2 from 0 to 2. Sub a 2 in, you get 4 minus 2, which gives you 2 pi. Okay, so far we've just looked at x and y axis. This is day 1. It's going to pick up a little on day 2. I have 1 down here where it's a little different, x equals 2. So let's look at this problem. I'm going to go over this one kind of quickly because it's similar to the ones above, and then we'll jump to something different. Okay, so graphing this one. Y equals 0 right here. X equals 2 right here. So we have this boundary and this boundary. Now plug sub a 0 in, you get 0. Sub a 2 in, you get 8. This is a parabola opening up. So the reason I put this one on there, even though it's a parabola like the other ones, is it's not always inside the bowl like this one was, how it's down. If this is your boundary, this is your boundary, and this is, you can see that this is your region. So if you revolve this around the x-axis, we don't need all this space. Remember perpendicular, so if this is your axes, here's your rectangles. So the volume, vertical, they keep coming on the x-axis, so they go from 0 to 2. These are x values, so I want x in here. The top is y equals 2x squared minus the bottom, which is 0. If you multiply that out, you get 4x to the 4th. You get 4x to the 5th over 5 from 0 to 2. Here's your scalar, 4 pi over 5. If you sub a 2 in, you get 32. 2 to the 5th minus 0. Multiply this out. Remember when you multiply by 4 to do that quickly, it's like multiplying by 2 and then another 2. So just double this twice. So 64, 128. So 128 pi over 5. Okay, now how does this change? Let's look at the same region, 2 to 8. We have this right here. Okay, now we're revolving around this line. If you look at this, this is just like the y-axis, but now this is our line. So I want you to treat it the same, use the same ideas. If this is the line of rotation, your rectangles go perpendicular. I'm going to use the calculator on this one. If the rectangles go perpendicular, we still have pi, that doesn't change. These go this way, they would go on the y-axis. This point was 2, 8, so they go from 0 to 8. These are y values. If these are y values, I need x equals. So I'm going to divide both sides by 2, and then take the square root. Okay, so if I want y's in my integrand here, then I need it to be x equals. So what's the right side? X equals 2 minus the left side, which is this function, which we already isolated at x for. And what are we forgetting? Two things. We want to square it and write dy. Okay, so this problem, more than anything, I want you to go back and look at. It's the same idea. I don't care what this is, if it's x equals 2 or 10 or negative 10, and we'll look at more of these as the chapter goes on. It's the same idea, right minus left. Think back to your 7-1 stuff, draw your rectangles in, and you'll be good. I'll let you type this into your calculator on your own. I got 16.755. Okay, wrapping up. So this next thing is pretty cool. The volume formulas for the shapes at the top of this lesson. So we looked at, let's see if I have it handy, like this right here. We know this. It's area of the base, so area of a rectangle times the height. We could do this, or other geometry class formulas, or even optimization related rates. Remember we looked at cones, spheres. They're derived from calculus. So let's see if we can figure out the volume of a sphere using calculus. Think about a sphere. If you take a cross section, so look back here. A cross section is a slice. So here's a slice. This is a rectangle. Who knows what this is? Some kind of weird thing. But all of these are slices. If you take a slice out of a sphere, you're going to get a circle. So let's draw a circle. We don't know much about this circle, so we're going to give it a radius of r. The equation is x squared plus y squared equals r squared. We're centering this at the origin to make it easy for ourselves. If you solve for y, you're going to get plus or minus the square root of r squared minus x squared. Okay, so y, that means this top part is the square root of r squared minus x squared, and the bottom is the opposite of that. Okay, so volume. We can't have all four of these quadrants spinning around because they'll hit each other. So maybe let's look at this top part and have this spin around. So the volume, we're going to have pi. Okay, now our rectangles, again, I always like using x if we can. Let's have them go from top to bottom, top to bottom, top to bottom. So the top function is this. So backing up though, these go from negative r to r. So let's get rid of that 0. We could double it too. We'll do that in a second, but I want you to see this setup first. So the top function is the square root of r squared minus x squared. The bottom function, so this is what y is, the bottom function is y equals 0. We're missing r squared and our dx. Now, due to symmetry, instead of going from negative r to r, how about we go from 0 to r and double it? So we get 2 pi from 0 to r. And then 0 becomes irrelevant. The square knocks out the square root, and you have r squared minus x squared. Remember, r is a number, so when we integrate with respect to x, this becomes r squared x minus x cubed over 3 from 0 to r. If we sub an r in, you're going to get r cubed, because r times r squared, minus r cubed over 3. If you sub a 0 in, 0 minus 0 is gone. Okay, moving this over. So now this is really, if we get common denominators, this is 3 over 3. 2 pi is our scalar. Oops. So 3 over 3 minus 1 over 3 is 2 over 3. One last step and we're done. 4 pi over 3 r cubed. And there is our volume for a sphere. That's a big smiling face. That was pretty cool. Okay, so this wraps up. You can see how all of this works. Volume, if you know 7-1, I said you'd be okay on 7-2. So just practice these and we'll move on to some more stuff tomorrow. See you guys.